Have you ever looked at a picture of Mount Everest and just been completely awestruck by its sheer size? It's the king of all mountains, the highest point on our planet. But have you ever stopped to wonder, how did it even get there? How does a mountain grow to be nearly 9 kilometers tall? The story is absolutely epic. It's a tale of continents smashing into each other, of oceans disappearing, and of forces so powerful they literally buckle the Earth's crust. Today, we're going to journey back in time, millions of years, to witness the incredible birth of the Himalayas and their crown jewel, Mount Everest. To understand how Everest was born, we first need to take a quick trip even further back in time, to about 200 million years ago. Back then, the world looked very different. There wasn't an India sitting below Asia. Instead, most of the land on Earth was clumped together in a giant supercontinent called Pangaea. Imagine all the continents we know today, all squished together like one giant puzzle piece. But the Earth's surface is not static. It's broken up into huge pieces called tectonic plates, which are constantly, slowly, drifting around on the semi-molten layer of rock beneath them, the mantle. Over millions of years, this supercontinent, Pangaea, began to break apart. The piece that would eventually become India started a long, lonely journey northward. For about 100 million years, the Indian plate drifted across a vast ocean called the Tethys Sea. Think of it as a massive continental raft, cruising along at a speed of about 9 to 16 centimeters per year. That might not sound fast, but in geological terms, it's like a sports car. This was one of the fastest plate movements ever recorded. As the Indian plate sailed north, it was on a collision course with the massive Eurasian plate, which forms most of Europe and Asia. Now, you might think, what happens when two continents collide? It's not like a car crash, where things just crumple. This is a battle of titans, playing out in ultra-slow motion over millions of years. And the first sign of this impending collision was happening beneath the waves of the Tethys Sea. The Tethys Sea wasn't just empty water. Its floor was made of denser oceanic crust. As the Indian plate moved north, the Tethys seafloor was forced underneath the Eurasian plate in a process called subduction. Imagine pushing a rug against a wall. The rug buckles and slides underneath. As this oceanic crust subducted, it melted, creating immense volcanic activity along the southern edge of Asia, long before the Himalayas existed. The Tethys Sea, which once separated these two landmasses, began to shrink. Its waters slowly squeezed out as India drew closer and closer to Asia. The fossilized remains of marine creatures found high in the Himalayas today are the silent witnesses of this long-lost ocean. Finally, around 50 to 60 million years ago, the main event happened. The Indian continental plate made contact with the Eurasian continental plate. This wasn't just a gentle nudge. This was the beginning of one of the most powerful geological events in our planet's history. Here's the crucial part. Continental crust is different from oceanic crust. It's lighter and more buoyant. So, when these two continents met, neither one wanted to be pushed underneath the other. They were both too thick, too light. Instead of one subducting smoothly, they crashed, crumpled, and buckled. Imagine two massive bulldozers hitting each other head-on. The ground between them would have nowhere to go but up. That's exactly what happened. The immense pressure from the collision caused the rocks along the plate boundary to fold, fault, and thrust upwards. The edge of the Indian plate was forced slightly under the Eurasian plate, but mostly, the crust just thickened and rose. Kilometers of rock, which were once flat plains or part of the Tethys seafloor, were squeezed and uplifted, beginning the monumental process of mountain building. This zone of collision and uplift is what we now know as the Himalayan mountain range. The initial collision was just the beginning of the story. India didn't just stop. It has continued to push northward into Asia ever since, and it's still pushing today at a rate of about 5 centimeters per year. This constant, relentless pressure is the engine that continues to drive the Himalayas, including Mount Everest, higher and higher. It's like a slow-motion geological traffic jam that has been going on for 50 million years. The rock that makes up Mount Everest itself tells a fascinating story. The very top part of Everest, the summit pyramid, is actually made of marine limestone. That's right, the rock at the highest point on Earth was formed at the bottom of the Tethys Sea. It's called the Komalangma limestone. Below that, you find layers of different metamorphic rocks that have been transformed by intense heat and pressure. You have schists and gneisses, which were once sedimentary and granite rocks, now warped and folded from the incredible forces of the continental collision. This layering shows us exactly how the mountain was built. Seafloor sediments were scraped off, buried, cooked under pressure, and then thrust violently upwards to form the highest peaks. So, how fast is Everest actually growing? For a long time, scientists have been trying to measure this. Using GPS and satellite technology, they've found that the Himalayas are still being uplifted. The rate of uplift for Everest itself is about 4 to 5 millimeters per year. That's about the thickness of a coin. It doesn't sound like much, but over 1 million years, that's 4 kilometers. This growth is the direct result of India continuing its slow but unstoppable push into Asia. But there's another force at play: erosion. While the tectonic forces are pushing the mountain up, the forces of nature are constantly trying to wear it down. Wind, snow, ice, and especially glaciers are powerful agents of erosion. The famous Khumbu Glacier on the slopes of Everest is like a giant conveyor belt of ice, slowly grinding away at the rock, carving out valleys and sharpening the peaks into their iconic jagged shapes. The pointed, pyramid-like peak of Everest, known as a horn, is a classic feature formed by glaciers eroding the mountain on multiple sides. So, the height of Mount Everest is a delicate and dynamic balance. For now, the uplift is winning, and the mountain continues to grow. This battle also makes the region incredibly geologically active. The immense pressure building up between the plates doesn't just push up mountains. It also gets released in the form of earthquakes. The devastating earthquakes that occur in Nepal and the surrounding regions are a tragic and powerful reminder that the forces that built Everest are still very much alive and active today. The official height of Mount Everest has been a subject of debate and remeasurement for decades. So, the next time you see that majestic peak, remember the incredible journey it represents. It's a story written in rock and ice, a story of a lost ocean, a continental voyage across the globe, and a collision of such epic proportions that it wrinkled the face of our planet. Mount Everest isn't just a static piece of rock. It's a living, breathing mountain, a monument to the immense and ongoing power of plate tectonics. It's a reminder that the ground beneath our feet is not as solid as it seems, and that the history of our world is one of constant, dramatic change.